and mechanisms. So as you will start to build, as we continue to do practice on these, it's not going to be so much just adding curved arrows. You're going to have to predict what arrows to use because you need to be able to predict the product. So this first step is probably the easiest one to predict, so let's take a look at it. We'll look at it a little bit more carefully. Pretend we don't have anything else. So if that is all you're given, what should you be thinking about? Why acid base? You see H+. Okay? So said another way, what you are looking for is the most reactive thing present. The most reactive thing present in this system, or this drawing right now, is H+. Why is it the most reactive? It's charged. Okay, so what do you need to stabilize a positive charge? Where are the most reactive electrons in the other structure? The lone pairs on the oxygen. There's your arrow. Now you predict your product. Okay? So we keep going back to finding charge, because sometimes it will be obvious, sometimes it won't be. So what you need to be able to do is start to think about why are we drawing the reaction as we're drawing. In the next step, you should be seeing that our electrons need to go up to the oxygen. Why do the electrons need to go to the oxygen? It's positively charged. We want to stabilize that positive by giving it electrons. In the next step, what happens? This one's harder. What hydrogen? Oh, it is shown. Never mind. I thought it wasn't shown. We're going to take the electrons that hydrogen has and shift them over to the positive charge. Where are those electrons located? In the bond between the carbon and the hydrogen. What you would have to show in sampling is then that arrow going to the carbocation carbon. Okay? That is a difficult thing to look at in grade. So when we talk about it in class, we'll add our little curly Q to it. Our curly Q is to represent that we're doing a rearrangement. Okay? So it's a slightly different system. The result is that carbon now has picked up an extra hydrogen and has now lost its positive charge, but the other carbon where our hydrogen originated from is now positively charged. Okay? Why would we do that? Okay? We're trying to stabilize the positive charge. And instead of going out into the solution to find a negative, we find something negative inside the structure. Why? It's easier. It's next to you. Okay? It's part of the atom itself, or part of the structure itself. It's easier to find those electrons within than it is to find them without. Okay? So we will see this rearrangement occur, and it stabilizes that carbocation. Okay? Now what happens? We find our negative and positive, we hook them up, and we connect, which eventually maybe the arrow will show in over the top. But as good. Okay, so now let's go through and label the type of mechanistic steps. What happened in that first step? Strictly acid-base. Next step. This is a heterolysis. All we are doing is breaking a bond. Yes, water leaves the structure, and water could be a nucleophile. But I can't do a nucleophilic or nucleophile elimination. Why? If we do an elimination, what has to happen? You have to form a double bond. There is no double bond forming, so it can't be a nucleophile elimination. Okay, so it has to follow under one of those other categories. The next one, kind of a weird one. We would classify it as a rearrangement. It's a little bit odd because it's not part of our standard mechanistic steps. Okay? Our rearrangements are kind of outside that class. They're also going to be outside of that class, or radicals will also be outside of that class. Okay, but what we've got there is really a rearrangement. Last step, what's happening? Coordination. What's that? I don't understand what you mean by chemical shift. Oh, 1,2 hydride shift is a more specific way to reference the rearrangement. Okay, and in this case, yes, it is a 1,2 hydride shift. If we go through to look at our energy diagram, we can start with our reactant. I don't really know where everything else is, so I'll just start with my reactant there. First product, charged, uncharged. We compare that to my starting material. Okay, uncharged. So my first product should be higher in energy. Okay. Next product, still charged, which means it should be higher in energy than my reactant. But how about in comparison to the first intermediate? It's a little bit less because oxygen is more electronegative than carbon, meaning does it want to be positive? No. Carbon would rather be positive in comparison to oxygen. It's always a comparison, which means that species is slightly lower in energy. The next one, still charged, but we're looking at a second or a tertiary versus a secondary. Tertiary is more stable, which means even less charged or lower in energy. And our final one should be even lower for our final product. The real trick now is how does that relate all the way back to our starting material? I'm not too concerned on that as long as you're saying it's coming out even or lower than. Okay? Why? It won't happen necessarily if it's higher in energy. Okay? Now what we could go through and do is connect these. One thing to watch out for. It is not being connected like this. Whoa, come on. Like this. Why not?
Because that's not how it works.
Not quite not how it works, but I mean that's sort of true.
Because you need peaks between each.
We need a peak between each of our reactants and products. Otherwise, that species never exists. Okay. Why do we need those peaks? If each of those points was a peak, okay, envision it as we're taking a little bouncing ball, and we can drop the ball in there. Okay, if I put the ball on the side of that hill, where does the ball roll?
Down.
Towards the reactants. Okay, so really what I've got at that point is now just a reactant. Okay, let's take the ball and I put it up here. Now where does it roll? Forward to a product. Something that exists as a product. How do I know it exists? Because in my mechanism I drew it as an individual structure. Okay. If that is now just a peak, if I now connect it like this, what happens when I put the ball here? Rolls down to the reactants. I've never formed that first product, okay, or that intermediate. We need to have that energy of activation between each of our reactions to show that that species now exists. Okay? Questions? Okay. Last thing that happens in Chapter 7 is they reference an exceptionally important intermediate known as the Keto-Enol. There's a couple different places where it shows up. It is primarily important in second semester OChem, and anybody taking biochemistry, roughly 80% of the chemistry you see in biochem is due to the Keto-Enol Tautomerization. Right? You right? Yeah, sure, why not? Okay. So what is happening in this situation? If we take this structure, okay, what you'll notice is that we have a resonance contributor. Those two structures are possible. Okay. What is special about both of those structures? They both have negative charge, which means both of them can act as a base. Okay. But if they act as a base, do we get the same answer?
No.
Our structure looks slightly different. Okay. So what ends up happening is we've got this issue of deciding which of those species is our preferential one, which one actually comes out of this. Okay. And it turns out that when we run this reaction, we always find that the carbon picks up the hydrogen and not the oxygen. Okay. Kind of a bit bizarre, okay, but that's the way this reaction works. Okay. We could go through and try and come up with other weird analogies on what's going on with that, and I kind of want to save that for second semester and stress about it then. Okay? Ultimately, really the only way you can go through and check this is by looking at the energy of each of the individual bonds that are different between the two structures. Okay? And if you sum up those energies, you notice that the energy of our keto form, which we'll talk about, is a little bit higher in energy, which means it's overall lower in energy as far as the structure goes, which I know sounds weird, but that's what it means. Okay? Because what we're looking at is the energy necessary to break those bonds. It requires more energy to break the bonds here, which makes that structure more stable. All right? One of the references I dropped in up at the top is Keto-Enol. What does keto sound like? Ketone. What functional group do we have here? A ketone. Enol sounds like? I could run with a phenol. Ene is the name for a carbon-carbon pi bond. There's our alkene. The OH, alcohol. What is the enol? It's the alkene with an alcohol on it. So when we look at a ketone, it does have some part of its structure, or some part of its total solution, comes out as the enol structure. The chemistry of the enol is dramatically different from the ketone functional group, and we can do all sorts of crazy weird stuff with the enol. It just happens that the enol form is very, very unstable, so most of it stays as a ketone. So what ends up happening is that we have an equilibrium between these two reactions. It goes back and forth between these. Ultimately, most of it goes towards the ketone. But if I now throw in, say, a weird reagent that reacts selectively with the enol, what happens? The enol concentration drops. What does the equilibrium do? Shift to reform the enol. So some of the ketone concentration shifts over to replacing the enol. But now what happens with the enol with the reagents I've added? Reacts again. The enol concentration drops again. What does our equilibrium do? Shifts again to the enol. Right? And so what we end up doing is taking advantage of a very poor equilibrium between those two products, or those two materials, to favor some chemistry that's happening out on the alkene, or the enol structure. Kind of a neat little process. Again, you'll see it a lot more in second semester. It does pop up when we look at addition reactions. Yes? The right one is your keto form. The red one is your keto form because it's a ketone functional group. The blue one is our enol because we have...
So that text above it, the red bonds are different.
It's interesting. I never actually read that.
Yeah.
I'm not quite sure what they're trying to say by that. They could just be saying the blue bonds are different in the blue form than they are in the ketone. It's a kind of a confusing way to reference that. I've never noticed that. Yeah, so because that's confusing, there we go.
Now I get it.
Okay? Now we don't have to worry about that. So we still have the enol in an equilibrium with our ketone. Okay. Common question that pops up, is this resonance?
No, because the atoms are bigger.
Okay. This is a common mistake made by lots of people. I've talked to educators that refer to this as resonance. This is not resonance between the ketone and the enol because we've changed the location of a hydrogen atom. There is a hydrogen on the alcohol that is not attached on the ketone. You've changed your sigma bonds. You do not have resonance. Okay? We do have an equilibrium. It's very important. Okay? This equilibrium becomes so important that we actually reference it as a tautomerization, not resonance.
What
Yes.
makes a tautomerization?
This process. So you'll see a tautomerization happen not with just carbon-oxygen double bonds, but with other double bonds in reference to nitrogens. You won't see it with carbon-carbon double bonds because in that case, it's just resonance. Okay? If we have a nitrogen as a double bond, we have a new type of form that's effectively the Keto-Enol Tautomerization, except you have a nitrogen instead of oxygen.
So it's just the rearrangement of the double bond and then the movement of
Yep.
that one hydrogen.
Exactly right. Okay? So that is the end of chapter 7. I'm kind of nervous as to how far we're going to get through chapter 8 today because I don't have all of it ready. So we'll see what happens. When we move into chapter 8, we're now going to be concerned about ultimately two types of reaction, the substitution and the elimination. Okay, so we can erase our acid base. We'll actually come back because the acid base does show up again. But we're really just looking at these two types. And in particular, what we're concerned about, wow, I knew it was a new topic and all, but dang, he was getting awfully excited. What we're concerned about with each of these reactions is now how does the substitution occur? How does the elimination occur? Okay? And if there are different ways for it to occur, is that relevant? Do I even care that there's different ways for it to occur? Because maybe it doesn't matter. It doesn't change the end result. Okay? But ultimately, this is what we're looking at, the balance between these two. Okay? And unfortunately, as you may or may not guess, the how it occurs, yes, there are multiple ways, and yes, it is important to distinguish between those two different methods. Okay? So in this chapter, again, we are not asking you to predict yet. What we are asking you to do is say, this runs under this mechanism, provide the products, the intermediates, the mechanism under this mechanistic condition. Once we move into chapter 9, then you get to predict. Okay? And that prediction is going to involve evaluating the things that can change. Your substrate, your leaving group, the nucleophile or base, and the solvent. Those things are going to dictate which mechanism occurs. Okay? So, substitution, possible mechanisms. Well, before we even really get into just drawing out mechanisms so you can now have something extra to memorize, it may be helpful to look at your structures and say what changed. Because if you can identify what changed, you can now simplify the how it changed. Okay? So, what things changed? Don't tell me substitution. Bonds broken and bonds made. We broke the CI. Is there anything else that happened? We made the CL. Okay, this is kind of neat. Only two things happened. Okay? So now the question is, how many possible ways can these two things happen? Okay? And the analogy that we come up with here is looking at two coins. We got heads and tails. What are the possible combinations that can come out of heads and tails? We're doing a similar thing with these two possible things happening. Okay? And yes, thanks for jumping ahead, there are three possible ways this can occur. What's one way it can happen? There is no illustration of how it happened here. All this shows is what happened. Okay, we broke a bond and we made a bond. So now the question is, how and when did those things happen? So we can go through and say that both of those things happen simultaneously. So we can break and make our bond at the exact same instant. Okay? So simultaneously. That is one option. Yes, I'm placing these in very particular numbering orders. What is another option?
The bond forms.
Okay. We can form the bond, then make the bond. Whoops. Oh, break. Yeah, I switched up my terms. Dang it. So we can make our bond. I'm trying to make it color coordinated. We can make the bond and then break a bond. What's the last possible option? Participation is 9/10 of the answer. break and then make. So before we now actually take these terms and convert them into a mechanism, we want to evaluate these a little bit closer and say, do I really need to look at all three?
No, the third one probably won't.
Why will the third one probably not happen?
It'll exceed the octet.
If I make the bond between the carbon and chlorine first, how many bonds would that carbon have around it? There's an implied hydrogen. If I now make that, I have how many bonds? 5 bonds. That is not possible. I've exceeded the octet. That's not allowed, which means we don't need to worry about that last step. So guess how many? Never. You will never worry about that last one. Okay? And I can confidently say that. You will never worry about making then breaking.
So, isn't there only 2 ways it can
So there are only 2 ways that we can do a substitution reaction. Might be backpedaling on that, never. There are only 2 ways that we can do a substitution reaction. Okay? We can either break the bond, then make a new bond, or we can make and break them at the exact same instant. Okay? So if these were then substitution reactions, we could now start to come up with a name. We have a substitution reaction of type 1 mechanism and a substitution reaction of type 2 mechanism. Okay? Guess how many substitution mechanisms there are?
2.
There are 2, known as SN1 and SN2. Okay? We added an N into that. What did that N mean? What is that chloride acting as? In this case, it's acting as our nucleophile. Okay? So we're doing a substitution reaction involving a nucleophile. We now have an SN type reaction, right, with 2 possible situations coming out of this. Okay? What happens if we look at an elimination? Okay? What are the things that change here? I heard reference to the pi bond. What about the pi bond? Okay, we make that pi bond. We break a carbon X. What else do we do? We also have to break a carbon H. This might be a little bit dangerous, because if we look at this now, how many things happened? Don't give me a lot. It's not quite that bad. 3 things happened. We broke 2 bonds and we made a bond. Okay, so we would, in theory, go through the exact same process that we just went through with the substitution and look at all the possible combinations out of that. Okay? With 3 different things happening, we're going to get a lot more options. Okay? Before we panic, is it possible, and of course the answer is yes, to ignore one of those things? What did I just draw? Even my Gen Chem class would give me this one right away. They've been shutting out every time. I regret telling them this. What did we just draw? It's a resonance structure for our product. Literally, every answer, every question I ask, they say resonance. Not an organic yet. Okay, we have a resonance structure. Why is it important to look at this resonance structure? What happens if I break the carbon X bond? Where are the electrons going to go? To the X. Why? It's more electronegative than the carbon, which means the carbon carries what charge? What happens when I break the carbon-hydrogen bond? Where are the electrons going to go? Why to the carbon? It's more electronegative. What charge does the carbon become? If I just break the bonds, what do I generate? The resonance structure for the product. I don't have to reference the formation of the pi bond because the resonance structures are identical. That is our definition of resonance. Both of these structures represent the same compound. If I just break the bonds, I end up with that resonance structure. So that means I don't have to worry about making the pi bond. Making the pi bond is necessarily going to come out of breaking carbon X and breaking carbon H. Which means when I now look at the possible things to evaluate, I only have to look at breaking X and breaking H. Okay? So we still come back to the idea of just two things are really changing. So just like we did with our substitution, we can come up with the possible options. We can have our carbon X or our leaving group leave, so we break the carbon X bond, then we break the carbon H bond. The net result is the formation of the pi bond. Or we could have them happening at the exact same instant. Or we could have the carbon hydrogen broken, then the carbon X. Okay? That last one gets a little bit trickier. Okay? When we looked at the substitution, we could eliminate the last option because we exceeded the octet. Do we exceed the octet? Okay? By breaking that hydrogen off, we don't exceed the octet of that carbon. It is perfectly happy being negatively charged. Right? It would have a negative charge, but it's not exceeding the octet. It's not invalid. Okay? So what we then have to evaluate a little bit closer is that carbon-hydrogen bond. What type of bond do we have between carbon and hydrogen? It is sigma, and it is single. Keep going. It is a nonpolar covalent bond. What type of bond do we have between carbon and X? Polar covalent. Which of those bonds should react first? The polar covalent, because of that dipole. We have a difference in a reactivity. The only reason we can break that carbon-hydrogen bond is because we can stabilize the forming positive charge on the carbon of your carbon X. That's it. Okay? So that really puts us in the situation that step 3, or option 3, also not a very good option. Okay? If you don't believe me, that's fine. You don't have to believe me. Just accept that there's 2 options for elimination. If you really want to, you can take it to 3 and make your life more difficult. So we got 2 options. What is the similarity between substitution and elimination? Very, sort of. I'd like a little bit more detail than that. What happened in substitution type 1? We broke the leaving group first. What happens in elimination type 1? You break the leaving group. Okay? Then we break the hydrogen. What happens in substitution type 2? They occur at the same time. What is happening in elimination type 2? They're occurring at the same time. Anybody see how this might be problematic with these 2 reactions?
Yes.
A very subtle change in the reaction conditions can take us from being a substitution reaction to being an elimination reaction. And on its own, that's not that big of a deal, except how different are our products? Very, very different. So you have to be able to look for those key differences and how that sets up what your product will potentially be. Okay, so keep that in the back of your mind as we're going through and looking at each of these reactions. All right? So the next part of this would then be going through and looking at our mechanisms, looking at what types of things contribute, and what you'll find or start to see hopefully right away is that within all of these possible 7 types of steps, we only have to worry about the first 3. Okay? Well, not quite. First 3 for sure, and then we also have to worry about the electrophile elimination. Okay? So SN2, E2, nice and straightforward. They're all on their own right up at the top with everything happening at once. How do we get in SN1? We break, and then we make. There's our SN1. What happens for the E1? We break, but we don't coordinate, because that means we're making a bond. What are we doing? We're breaking another bond to make a pi bond. What type of reaction makes a pi bond? Elimination. Okay? So those are kind of our ideas behind balancing these out and drawing those connections and parallels. Okay, so let's take a look at our SN2 and our E2 happening at the same time. So if we were going to add curved arrows into this, okay, we take a look at that first reaction. What's the most reactive thing you see? Why is the iodine the most reactive thing you see? It is negatively charged. The sodium is positively charged. Why do you not look at the sodium? It is always positively charged, but every atom, as far as organic chemistry goes, does what with the electrons when bound to sodium? Takes them away. Which means, is the sodium going to do anything?
Not really.
No. Think back to, I know you're going to love doing this, think back to your solubility rules in 152 and 151. What was rule number 1? Anything bound with sodium is soluble, which meant that when you looked at the total ionic equation, you could cross it out because it was a spectator ion. The only reason sodium or any of your metals are really included in any of our reactions is to hide a negative charge. Why? Because it's too easy if we give you the negative charge. Okay? So don't fall for that trap. As soon as you see it, drop your negative in, cross your sodium, cross your metal out, you're good to run. Okay? So we have a negative charge on our iodine. What do we need to stabilize that negative iodide? Positive. So what do you have to find? The most positive atom possible. What's going to make an atom positive?
Lack of.
We could do lack of electronegativity, but that's not going to be it. A difference in electronegativity between what our atom is that we suspect as being positive and to the things that are attached to it. So we look at that structure and we say, there's a carbon that is partially positive. Which carbon is partially positive? The one attached to the bromine. You guys are doing this way too fast. Okay? Why? Not why are you doing it too fast, but the difference in electronegativity between the carbon and the bromine, bromine's taking the electrons, carbon becomes positive. What did we do? We found our most negative and we attached it to most positive. That's everything we do. What's the net result? What happens as we do that electron pushing? It's not officially substitution quite yet.
The electrons from the carbon and bromine bond.
Why are you looking at the electrons between the carbon and the bromine? We've exceeded the octet by sharing those electrons. It goes all the way back to Lewis structures and not drawing these pentavalent structures. It's not possible to draw that result. So before we move to drawing our products, we have to satisfy the octet. To do that, electrons need to be moved away from the carbon. Why? So it doesn't exceed its octet. If we move those electrons towards the carbon, we got a problem. So let's take the electrons. Where are those electrons located? In the bond between the carbon and the bromine, and we'll push those electrons towards our bromine. The net result, we've done our substitution. You'll notice at the end of this that sodium came back into this. And you'll also notice that there is no arrow referencing the sodium. Why is there no arrow referencing the sodium? It's a spectator ion. Why is it showing back up in this? Because everything that we told you in Gen Chem not really was a lie, but all the organic chemists hate that process because what you had to do with every single equation was balance it. Oh, you don't have that sodium. Oh, now you're all wrong because it's all balanced. I don't care about the sodium because sodium's not connected to carbon. And this is organic chemistry, and all I care about is carbon. Okay? I will personally try my best because I'm aware that everybody wants these balanced equations. I will try my best to balance them. Guaranteed I will fail miserably at that. Okay? So if you see it and you need it balanced, let me know and I will try and do my best to draw your attention to it. Okay? So we now have our balanced equation with our swap around. There's our product. There's our substitution. What happens in the elimination?
The pi bonds form.
What did we say about the pi bond? The pi bond is a secondary thought. The pi bond does not form on its own. Okay? Everything else happens which causes the pi bond to form. So what's the other stuff that happens? We break the bond between our carbon and leaving group. Okay, why did we break that bond? Okay, it's a good leaving group. The leaving group wants to take electrons. It's more electronegative than the carbon, so it's sucking those electrons away. Okay, what else happens?
The electrons from the base attack that positive charge on the carbon.
Okay, let's draw that in there. If the base comes in and attacks that positively charged carbon, what happened?
Takes the hydrogen.
Forms a bond between the base and the carbon. Is that what we're saying the base needs to do? No. What does a base do? Forms a bond with hydrogen. Where is that hydrogen? It's implied at the next position over. Now where do those electrons go? Well, our hydrogen has too many electrons around it right now. So we have to get rid of some of those electrons. Where do they go? We could have them go to the carbon. Okay? And it's kind of a rough approximation, that's okay, but ultimately our net result is trying to make the pi bond. So instead of putting the electrons on the carbon, let's put them to the bond where our pi bond forms. Okay? Elimination reactions are often referred to as beta elimination. Oh my gosh, beta, Greek letters. It's always a time to panic induce. The first chemistry we referenced here was at that carbon. Right? That carbon we would probably specify as what carbon? Carbon number 1, but if we can't speak in numbers, we can use our Greek letters and it would be alpha. The carbon where our hydrogen was removed? Beta. What's happening? It's a beta elimination. Why are we referencing the beta position and not the alpha? Which bond is harder to break? Why is the beta position harder to break? What type of bond is at the beta position? A nonpolar covalent bond. What position is at the alpha? Polar covalent. Which bond is easier to break? The polar covalent. So the harder bond that we're concerned about is at the beta position. That's why we're referencing the beta position. Okay? Why do we go through and pull that hydrogen off? Well, we could not look at that quite yet. Let's take a look at the E1 mechanism. Okay? We can look at these, sorry, that was a bad jump. Do you guys have questions on that now that I erased all the arrows?
So if it's harder to break that bond between the carbon and the hydrogen, why would it want to do that?
Because the net result is making the double bond. Okay, we make that pi bond, and it's going to be an even bigger issue. We stabilize the base. So in the E2 mechanism, the base that we use is very, very strong. So you'll notice that I've got an M/H. Any ideas what those terms mean? Metal and hydrogen. Why am I specifying it like this? Because in this case, I haven't specified what mechanism I'm actually doing here. This is my generic format. So in the generic format for an elimination, your basic atom can either be attached to a hydrogen or a metal. In the E2 mechanism, you'll find that needs to be a stronger base. What should the base be attached to be a stronger base? The metal, because all of our metals have low electronegativity, which means the basic atom will take the electrons, becoming negatively charged, which is a strong base. So the driving force for our elimination here is that we're neutralizing that negative charge. Once we put the hydrogen on, no longer charged. Okay, so it is an exceptionally hard bond to break. In the stepwise mechanism, both E1 and E2 are following the exact same process. We are breaking our bond first through a heterolysis. The iodine in this case leaves the structure, leaving us with what product? What the heck? Oh, never mind. What is a good answer? That means you didn't see what I did. But I think the bottom shouldn't have shown up either. Okay. And a heterolysis, if we follow that arrow pushing, what was our result? We end up with a carbocation, now a free iodide, and in this case we can reference chloride. Okay. The biggest difference between our elimination and our substitution in this type 1 situation is what happens next. Okay. So take a look at these two reactions. What happened in each of those reactions? What type of mechanistic step? It's a hint. It's not substitution. It's not a mechanistic step.
Coordination.
One of them is an electrophile elimination, and the other one is coordination. As you might guess, that's hinted at the very top of the slide. Sometimes I give you information, not always. Okay. Which one's which?
Coordination is well, you're right.
Our coordination is happening on the left, and on the right, we're getting the elimination. Okay. Just because we're kind of getting a peanut gallery making it sound like they understand everything. Not that that's bad. How's everybody doing with this? Everybody following it okay?
I can't see that in between, like, the arrows.
You can't see the arrows where? For 3 and 5?
Yeah, like,
Okay, we're going to add those in.
yeah, that's adding them in.
Okay. So now what we'll do, once we've got that process, so what I'm asking about is everything up to this point. How does everybody feel? Good, bad? Just hearing some okays and goods. This is going to be one of the misleading things in organic chemistry. What we just walked through and talked about were all of the answers and the questions that you should be asking as you solve a problem. When you go home, what are you going to be looking at in your notes? The answer. How many of you wrote down any of the questions that I was asking you to work through each of these? Nobody. Huh. So when you get to a new problem where you don't have someone like me asking you pestering questions, what happens? You have no idea what's going on. Okay? So what I need you to go through and do is be thinking about the questions that we're asking at each of these stages. That's the important aspect. That's the questions and the stuff that you should be writing down. Everything up on the PowerPoint is ultimately useless because you already have it. Writing it down isn't going to help you. Okay? So the next question here was, how do we move from our intermediate carbocation to each of these potential products? Okay? So let's pick one. Which one do you want to look at? 3 or 5? Really? We'll jump to 5 first. Okay, so let's take a look at 5 first. I'll accept it. Okay, and we'll even color, I won't color code. So what's happening in 5?
You're adding a new electrophile into it.
We have this H plus that's mysteriously shown up. Where did it show up from?
The bond between beta and carbon.
Something that can be helpful is to actually draw out all of your hydrogens in your individual structures. Okay, peanut gallery. Let's cut it out. Okay. Where did that hydrogen come from? Once we've got all the hydrogens drawn onto our structure, where's the hydrogen coming from? The only place it changed was there. Our purple hydrogen, which I guess I could have drawn as our black, was our H+. That hydrogen was somehow removed from the structure. Okay. Why did we remove that hydrogen? The positive charge is ultimately what is wrong with this structure. We need to stabilize that positive. How do you stabilize the positive? With electrons. So what we want to do is bring it electrons from wherever we can. And one of the things I would recommend you try and do is look at the closest sources of electrons. The closest source is going to be all of the bonds immediately around your carbocation. And what you will find is none of those bonds can stabilize that positive charge. Okay? It will physically be impossible due to orbital diagrams. Okay? So we have to move to an atom next door. When we move to that atom next door, our best source of electrons is breaking any one of those bonds to shift the electrons over. So now what happened to the electrons between the carbon and the hydrogen?
Which carbon?
Whoa, that was supposed to be an eraser. They are now located in the pi bond. Is there a bond between the carbon and the hydrogen anymore?
No.
No. So what happened to the hydrogen? It just sits there as H plus with nothing attached to it. Okay. Typically frowned upon in mechanisms. We usually want to show something pick up the hydrogen. What charge would our atom need to be to pick up the hydrogen? So what should we do? Look in our structure or look in our reaction to see if there's something else that can pick up the hydrogen. We've got that chloride or the iodide as a possibility, and instead of writing H plus, what we could be writing instead would be HCl. Anybody have any problems with writing HCl? What do you mean, would that ever form? It's a strong acid. Why would that ever happen? Answer is it doesn't really happen. How do we get that bond to break? We add a lot of heat. Okay, what is heat going to do to things? Cause them to move. If that bond starts moving more and more, eventually what happens? It breaks and the electrons slide in to form the pi bond. So under an E1 reaction, one of the signifiers or one of the tip-offs is looking for heat, because heat's going to help break that bond. Okay? Because in a lot of cases, we don't have a very strong base to be able to pull that hydrogen off. Because if we have a strong base, we're now looking at the E2 mechanism. Okay? Yes?
The one we talked about before, he used that H right there with the earth.
Yeah. This is our, whoops, I wanted black on that. Heat helps to break that bond off. Okay? What happens with the substitution? I'm going to erase everything.
Is coordination's not the same thing as substitution?
Substitution is a type of reaction. It is not a mechanism. Coordination is the mechanistic step of forming a bond between two species. Okay. So all that's happened is we've taken the iodide and we shared, the chloride, and we've shared those electrons with that positive charge. Okay. And we now have our coordination mechanism. In the other case, we had our electrophile elimination. What was the electrophile? Can't spell elimination. And I'm going to put electrophile in quotes. Our electrophile, what the was that guy? Was our hydrogen. Okay. How do we know it was an elimination? The formation of that pi bond is our elimination. Okay. So those are all four mechanisms, nicely summarized. Okay, all into one thing. Yes.
For coordination, what makes it favor the chlorine over the iodine?
That has to do with the strength of the nucleophile, and technically the chloride doesn't favor it, the iodide does. Okay. And what we'll do when we look at the strength of the nucleophile, we'll talk about that in Chapter 9. In Chapter 8, you're told, do it. So in this case, do it. That's how we know the chloride did it. Okay?
But really it wouldn't.
It really wouldn't.
Elimination, they're fine because it's breaking of two sigma bonds to form a bond.
Yes. Yeah. So the type of reaction, so we've got the types of reactions and the types of mechanisms, and there's some overlap between those names. So an elimination reaction, it's the breaking of two sigma bonds. So if we look at the overall reaction for our elimination. What happened? In that first step, we broke a sigma bond. There's broken sigma number 1. And the next one, it was broken sigma number 2. And the result was the formation of that pi bond. Does that make sense? Okay. Other questions?
When you went to the wedges and dashes?
Not yet.
Not yet.
Do we care that we have all these types of reactions?
No.
So what we've got is summarized up on top. Both of these are what types of reactions? Our substitution. And on the bottom we have the elimination. So we now have all of those reactions, their mechanisms ultimately outlined without the curved arrows. So you could add curved arrows to this. We could theoretically also go through and show energy diagrams.
But wouldn't they start in the same places?
No.
Not quite. Which reaction did I just show?
It would be the top substitution.
All right, so the first thing we should needle down is, can it be either of the middle two reactions?
No.
Why not?
Because there's two areas.
There's 2 peaks. Okay, so I need an intermediate. Okay, so it's either the top or the bottom. Why would it be the top and not the bottom?
Because it's lower energy.
This is where looking at the energy of your products can help out. We're looking at a lower energy product. Okay. What would I expect if this had been an elimination?
Higher energy.
That was kind of horribly drawn. Let me try that again. Why would it be higher in energy? Pi bond is higher in energy than sigma. Okay. How do we get this reaction to occur? We don't look at the overall energy of, or we don't look at the energy of just the carbon structures. We look at the overall energy of our reactants. And we end up adding a really strong base. A really strong base is very reactive, which means the energy of our reactants now goes up there. Okay. And now when we look at the overall reaction, we got a favorable situation. So we can change our reaction conditions by changing the activity of our individual reagents to look at slightly different energy diagrams. Okay, so between these two mechanisms, do we care? Philosophically, because this is a chemistry class, we absolutely care. But actually, chemically, do we care? Is this something that could potentially hurt us if we were looking at an exam? And dang it, I forgot my model kits.
Yes.
Why is it going to matter?
Because you have 2 different products.
Why do we have 2 different products?
Because the mechanisms are different.
In the case of our SN2, the nucleophile comes in, and you'll notice that I've been drawing the arrows just like this, right? The big important one is now in 3D, right? Blue and red. Okay. That is now our important arrow. Why is that arrow always drawn in this case in that direction? You'll notice
It wants to stay away from the leaving group.
I never show it coming in this way. What does the leaving group leave as? A negatively charged species. What does our nucleophile come in as? What happens when the negatives get near each other? They repel. So if the nucleophile can never make it into the carbon to form that new bond, no bond forms. Okay, so when we look at this reaction, that nucleophile must come in from the backside, okay, of that leaving group bond. It has to be. So that type of reaction always gets referred to based off the backside attack. What happens in the SN1 reaction? Do I care where the nucleophile comes in from?
No, because it's positive.
It's just positive. So there's no difference between those 2 arrows?
Yes.
What's the hybridization of that carbon? sp2. What makes it a carbocation? An empty p orbital with a lobe above and below the plane. If the chloride comes in and attacks from the top plane, the chloride is up. If it comes in and attacks from the bottom, the chloride is down. Does that change the product?
Yes.
Yes. Okay. When does it change the product? Okay. And as a big hint, I've given you two reactants here, or two products, where it is important. What is characteristic about these products? What is that special circumstance? I have a stereo center. Remember chapter 5? Chirality? Boom, comes back. This is where it's going to come back. If I run under an SN1 reaction, the chloride can attack, or my nucleophile can attack either from the top or the bottom, which means I get two products. The relationship between those two products would be, not resonance, enantiomers. If I take a look at the SN2 type reaction, how many products do I get? Only one, because there's only one backside of that leaving group bond. I get one product. If I'm trying to design a reaction, make some drugs, does that bother me? Yeah. If I only want one of those enantiomers, one of those molecules, and I run an SN1 reaction, my yield has now gone to 50% at best. Under SN2 conditions, I now have potential for 100% yield, or 0%, depending on what we were trying to get. Okay? So I want to be very careful with deciding what mechanism to choose, okay, or what reagents to choose between these. Do I run into a similar issue with the eliminations? It's kind of a weird one. Do we have a chiral atom in our products? No. So it's not chirality that's showing up. What's the issue? We have a cis-trans isomer. You'll notice for now our E1 type reaction, we can have cis and trans products. Why? I can freely rotate about the sigma bond in the intermediate. Which of those two products becomes favored? The trans is almost always exclusively favored because lower in energy than the cis. What product is formed in the E2? That one's trickier. It is either cis or trans, dependent on where the hydrogen was removed way back in our mechanism. Much, much harder to see. Okay? So the mechanism is of critical importance. Under SN1 conditions, we expect two products. Under SN2 conditions, we get one product. Under E2 conditions, we get one product. Under E1 conditions, we really get one product, and that one product is always trans. Okay? So all of these kind of subtle differences fall out of this. So we absolutely need to recognize that there is a difference between the mechanisms and make sure we address those differences. Okay? So we can identify or decide that these mechanisms are important by looking at the possible products that come out. There are other ways that we can try and evaluate this. One possibility is trying to isolate the intermediate in our SN1 and our E1 reaction. Can we find the carbocation? Problem with the carbocation? It's charged, which means it's unstable, which means it's reactive. The odds of me being able to isolate the carbocation? Close to nothing. Okay? So it is very difficult to prove that these mechanisms exist because I can't grab that species. I can't stop the reaction at that intermediate. Okay? It very quickly goes on to form our final product. So really all I can do is look at the final product balance and hope for the best. The other thing that we can go through and do when trying to prove a mechanism, think all the way back to 152, if you're trying to evaluate a mechanism, what do you need to look at? Rates. Kinetics. Yippee. Okay. So what I've got now in the slides is a quick kind of review of kinetics from 152. These are literally copied and pasted out of my discussion for 152. Kinetics, kind of the big overall summary slides. So if you've got questions on it, please address those questions right away. Okay? So when we're looking at reaction rates, we really have kind of a mathematical expression and an English interpretation of it. So for an individual reaction, A plus B goes to C plus D, our rate law for the reaction follows the standard form, rate equals our rate constant times the concentration of our reactant to its order times the concentration of the next reactant to its order, and officially times the concentration of the product to its order, concentration of the product to its order. Why do we typically ignore the products? It is very rare conditions where the products affect the rate of the reaction. Those rare conditions tend to happen in very complex situations, i.e. biochemistry. Okay? The superscripts must be proven experimentally for any given reaction. Okay? So we look at reactions as a whole. You have to prove what those values are. So at this point, we don't know what our mechanism is. So what we would have to do is go through and set up an experiment to solve for those orders. Okay? K is our rate constant, which we could solve out of our expression. M and N are our orders. Okay? So our order of our reaction is kind of the math. Okay? And what we're trying to do is bring in a chemistry interpretation of what that math means. So what does a number mean up there as far as our reaction goes? Okay? So if we look at the order with respect to an individual species, there's some numbers that can come out of it, and we can come up with a relative importance for each of these. So if it is 0 order, that molecule is not involved in the rate at all, because any number to the 0th power is 1. So that means that species has no involvement in the rate of the reaction. If it is 1st order, that species is now involved in the reaction. 2nd order, it's now becoming increasingly important, because as I change its concentration, it's now drastically changing the rate by a 2nd order factorial. Factorial is probably the wrong word. And then 3rd order, it's pretty much all about that one chemical and nothing else. Why is there no 4th order or 5th order or 6th or 7th?
Because you can't get higher than 15 going up the line.
Why? The best relationship I've come up for this is to actually use human relationships. Okay? 0 kind of sucks because then you don't exist. But 1, we get a lot of people as single people around in the world. That happens fairly frequently. Okay? 2 people in a relationship also happens relatively frequently. Not that big of a deal. We don't really kind of go, oh, well, that's crazy. 3 people in a reaction? Okay. Mind blown. That doesn't work. Okay. Those things just don't happen because we can't get 3 people in the same room to agree with each other for long enough to do much of anything. Okay, so it just doesn't make sense to exceed that 3-person limit. Same thing is happening with chemical molecules. We can't get 3 molecules to all interact with each other at an exact given instant. So we won't see more than 3 because that's just way too hard to get 3 different things to actually agree for long enough to do anything productive. Okay? If we switch this around to now the molecularity for the reaction, we take the sum of the orders. So we take the superscripts for every single one of our species in our rate law, and we just add those numbers up. If we get a 0 overall reaction, well, reaction doesn't exist. Nothing happened. Okay. If we get a 1st order reaction, or sum of our orders is 1, it's referred to as unimolecular, bimolecular, termolecular. Again, why do we not see 4 or more? It's way too hard to get that many things coming together at any given instant to get a reaction to work. Okay. Do we have to worry about termolecular? We don't even have to worry about termolecular. In organic chemistry, we're going to be concerned with unimolecular and bimolecular only. Rate laws. Okay, so once we've got a rate, we can sometimes use our equation to go through and predict the rate law. So if you notice with each of these equations, the rate law kind of matches your equation. In the first one, there was 1 NH4, 1 NO2 minus. The orders were 1 and 1. The next one, 2 Cl2, 2 OH minus. 2 and 1. Next one, NO2 plus CO, and NO2, 2, and there's no CO. What's going on with that? Those species don't affect the overall reaction. So certain reactions are simple enough where what you're looking at does directly translate into the rate. Okay? Some reactions as an overall don't work. So what we're looking at in each of those cases is an overall reaction. What we're going to be concerned about when we move to mechanisms is now not something referred to as an overall reaction, but instead an elementary equation or an elementary step. In those individual mechanistic steps, your rate will be equal, or your orders will be equal to the number of times it shows up in that mechanistic step. We can do a direct translation across, just like we did for the first reaction. Okay? Rate laws and rate limiting steps. If we go through and look at our reactions, we want to be concerned about our slowest step, because the slowest step is what's going to determine the rate for your reaction. So you could look at your whole process of trying to get to campus. And if we tried to change certain aspects of that, would that get you to campus any faster? Well, if it only takes you 2 seconds to wake up, okay, but it takes you 5 minutes to get here, waking up 1 second faster, sure, in that individual step, okay, you went twice as fast. How much did that change your overall answer?
Barely.
Barely at all. But let's say it takes you 4 minutes to bike here. Well, if you can cut that in half, that drastically changes your end result. Okay, so what we're concerned about is the slowest step in an individual reaction. What's going to be a signifier for a very slow step in a reaction?
The energy activation.
We can look at the activation energy. How do we decide the activation energy is going to be really big? We're doing an endothermic step of a reaction. That first step is going to be very, very big. Okay, so we're looking for that largest activation energy for each of your individual steps. And we can predict that because we probably started neutral here and we became charged up here. So we can look for that charged and neutral transition. It's not perfect, but it gets us pretty close to evaluating those individual things. Okay? Which we've already been doing. Okay? Questions? Good. So we'll leave you with this exciting stuff. Actually going through and trying to determine what type of, or what things, or sorry, let me try that again. Provide the rate law for this reaction. So we've got experimental evidence. What I want you to do is come up with a rate law for it. Okay? Shouldn't be too bad. I know we're done, so I'm not telling you to stop packing up, but that's where we will pick up with on